All right, here we go once again. We're diving into lesson 16, which is all about something called common factors. All right, let's look at our first activity. It says figures made of squares. Now, in your workbook, we have yellow figures and blue figures. So I will try to keep that in mind as we're doing this so that we can talk about the colors as well. If you have a black and white copy like me, then we'll just deal with the different colors of gray, but we do know that this is yellow and this is blue. Okay. All right. So in our first activity, it asks us how are the pairs of figures alike and how are they different? Well, looking at all of these yellow figures, I noticed pretty quickly that all of the yellow figures, while they look different, they all have 6 squares in them, right? These two were obviously, that's just knocked on its side, right? And then this one just has one more stacked up top, right? So I noticed right away that all of the yellow figures have 6. So I'm going to write that down as something that's the same. Okay, so all the yellow figures have 6 in them, and I just summarized it that way. Tell me about the blue figures. Well, I noticed that the blue figures all have 10 in them. Did you notice that too? They do. All of the blue figures have 10. So each figure in its entirety, if we take it as an entire figure, the figure itself all have 16 total squares in them. Okay? So that's one thing that's the same about all of them, right? Now, how are they all different? Well, I mean, it's pretty obvious how they're all different, right? Their heights are different. This height is 2, this height is 3, this height is 4, and this height is 5, right? Same with the blue ones. This height is 2, this height is 3, this height is, oh, look at that. Well, we can say that's the same too, though. These both have a height of 2, these both have a height of 3, these both have a height of 4, and those have a height of 5. So those are actually sameness of, let's see, heights of 2, 3, 4, and 5 respectively. That means in that pattern, right? Height of 2, height of 3, height of 4, height of 5. So those are all my sames, but they are different heights, are they? So we can write that as a difference as well. Different heights. Right? Different looks and shapes. Sorry about my big black line again. My printer, as it did a little while ago, my printer is having a hissy fit again today. I think it's time to change the ink. So those are some differences. I mean, I'm sure you found a lot more differences. So whatever you wrote down, I'm sure is great. Let's move on to activity number 2 now. Diego's bake sale. Diego is preparing brownies and cookies for a bake sale. He would like to make equal-sized bags for selling all of the 48 brownies and 64 cookies that he has. Organize your answers to each question so that can be followed by others. Okay, so we got to remember to be organized in our work here. Number 1, how can Diego package all the 48 brownies so that each bag has the same number of them? How many bags can he make? And how many brownies will be in each bag? Okay, so we need to organize our work here. We need to figure out how many bags can I separate them out into, and how many brownies will there be in each bag? And no matter how I do this, my handwriting is not so great today. And no matter how I do this, I need to use all 48 brownies every time. Now, in order to do this, we need to use something called factors. And I think we remember what that vocabulary word is. A factor is a number that when multiplied by another factor, we get a product, right? The factors are what we multiply in I can't talk and write at the same time, in a multiplication problem, right? So factors are what we multiply. For example, 2 and 3 are factors of 6. Does that make sense? Because I can multiply by 2 to get 6, and I can multiply by 3 to get 6. Okay, so 2 and 3 are factors of 6. Now, the other thing that I want to point out today is that this pair of numbers that equals our desired product is called a factor pair. Okay, because no matter how we write 2 times 3 or 3 times 2, it'll always equal 6. Together, those factors always multiply to 6. So that's a factor pair. So down here on this problem, what we're going to need to find are the factor pairs of 48. Okay, because if I split, for example, if I split this bag into, or this set of brownies into 6 bags, right? 48 divided by 6 is 8, because 6 times 8 equals 48. So that is a factor pair, because 6 bags with 8 brownies in each bag would give me my 48 brownies. Okay, well, there's a lot of factor pairs that will work for 48. So let's organize our work a little bit more than I just did and see if we can find all the factor pairs of 48. Now, the easiest way to do this is to start with the smallest number, which is 1. Now, 1 is a factor of any number, as we know. It's not a very useful factor, but it is still a factor. If I put all 48 brownies in one bag, of course, I'm going to have 48 brownies in that bag. And 1 times 48 does, in fact, equal 48. So it is considered a factor pair. Okay? The next number we should try is 2. Can I split 48 brownies evenly into 2 bags? Yes, I can, because 48 divided by 2 is 24. So 2 and 24 is another factor pair of 48. All right, now let's go to 3. Can 48 be divided by 3? And it can. Okay, so if we need to pull out our multiplication charts to help us with this, we can. 48 divided by 3 is, I believe it's 16. Okay, so 3 times 16, there's another factor pair to get to 48. Okay, how about 4? Does 48 divide by 4 evenly? It does. 4 times 12 is 48. To see how this is figuring all the math out for us, if I have 4 bags, they're going to have 12 brownies in each, and I'm going to use all 48 brownies. Okay, how about 5? Does 5 go into 48 evenly? No, we know it doesn't, because 48 doesn't end in a 5 or a 0, so 5 is out. How about 6? Yes, that's the one I found very first, right? We know that 6 times 8 is 48, so 6 and 8 are, again, another factor pair. Okay, now, what about 7? Does 7 go into 48 evenly? It doesn't, does it? And the next number would be 8. Now, I would be tempted to say 8 bags, and I could do 8 bags, and if I do 8 bags, then I'm going to have 6 brownies in each bag. So literally, it's the opposite. If I switch these two, it gives me this one, right? So for every factor pair, I don't really need to repeat them all. I just need to know that this can go either direction, can't it? I can have 1 bag of 48 brownies, or I could have 48 bags with 1 brownie in each, right? Now that's usually how bake sales work, right? Sell 1 brownie per bag, so that might be an idea. Or I could do 24 bags of 2 brownies each, or I could do 16 bags of 3 brownies each, or 12 bags of 4 brownies each, or 8 bags of 6 brownies each, right? But this, because I've now run into numbers I already used, I'm not going to find any more, right? That's all we've got. Those are all the possible ways of bagging up these brownies. If you remember, this goes either direction, right? Between bags and the number of brownies in the bags. Okay? So that's basically the answer for number 1. Those are all the different ways of bagging up the brownies. Okay? Let's do the same thing in number 2, but this time for the cookies. Okay, I'm going to keep these brownies kind of handy because we're going to need those in a minute. Now we're going to do the same thing with the 64 cookies. We need to know how many we can put in a bag and how many different combinations of bags we can make with the cookies. Again, we'll need to use all the cookies. So how many possible ways are there to package the cookies? Again, we need a number of bags and we need the number of cookies per bag, right? So once again, I could do one bag of 64. That's kind of a huge bag of cookies, but we can do it that way. We could do 2 bags, and that would have 32 cookies in it, in each bag, because 2 times 32 is 64. How about 3? Does 3 go into 64? 3 goes into 6 twice, but does 3 go into 4 evenly? No, so 3 doesn't go into 64. How about 4? Yep, 4 goes into 64. I believe it's 6 times. 16 times, my apologies, 16 times. Okay, so 16 times 4. How about 5? Can we do 5 bags? Nope, because 64 doesn't end in a 5 or a 0. How about 6? Does 6 go into 64? Nope. How about 7? Does 7 go into 64? 7 goes into 63, but not into 64. How about 8? Yes, we know that 8 goes into 64 because 8 times 8 is 64. Now, there's a very special factor pair where both factors are actually the same number. That factor pair right there is what turns into an exponent, right? This would be 8 squared. That's a perfect square factor pair, isn't it? Okay, so that's a special one. Okay, that's just kind of a side note there. It is possible to have the same number for both factors. How about 9? Does 9 go into 64? No, once again, 9 goes in there 7 times to 63, but not 64. How about 10 or 11 or 12 or 13? I think we'd have to keep going all the way up to 16, wouldn't we? And we've already got 16. So that's where we get to our switching, right? 8 and 8, once they're the same number, we're not going to find anymore. There's a big hint, okay? So now we know I can do 1 bag of 64, or I can do 64 bags of 1, right? These could go either direction. I could do 2 bags of 32, or I could do 32 bags of 2. Again, they could go either direction. 4 bags of 16, or 16 bags of 4. I could do 8 bags of 8, or 8 bags of 8. That's the one that's pretty straightforward. So now I've organized both my bags of brownies and my bags of cookies. And we see some similarities here. And this is where we're going with this activity. Let's read number 3. How can Diego package all 48 brownies and 64 cookies so that each bag has the same combination of items? So we want to put brownies and cookies into the same bag. That's what they're asking here. But we want them to have every bag like that to have the same number of both things so that everybody gets the same, right? One sister can't get 3 brownies and the other sister get 2. That wouldn't be fair, right? So we want them to be the same. So we need to figure out how many bags can he make and how many of each thing will be in the bags, and we want to find all the possible ways, okay? So the way we do this is we compare these 2 lists. Are there similarities in these 2 lists that we could use to help us? Well, of course, if we only package things into 1 bag and put all the cookies and all the brownies into 1 big bag, yeah, we could do that, and that bag would be the same. But that's not very feasible for a bake sale. Maybe for Costco or some other big box store, right? But not for a bake sale. That wouldn't work so well. Notice we could split it into 2 bags. And if I did 2 bags, I could do 32 cookies and 24 brownies. So that's one possibility. In fact, we should be writing these down. We can do bags. We could have 1 bag and it would have 64 cookies. I'm going to have to put brownies on here too now. And it would have 48 brownies. Okay? Or I could have 2 bags, and in the 2 bags, I would have 32 cookies and 24 brownies. They'll still seem a little large, right? 4 is in common as well. So I could do 4 bags with 16 cookies and 12 brownies, right? But that's not the only way we can do this. Remember, we can also go the other direction, right? So let's look at these numbers and see if there's anything in common and pretend that instead of being the brownies, let's pretend these are the bags now. Look, they both have an 8. So if I did 8 bags, right, I would have 8 cookies and 6 brownies. Do you see how I just flipped those backwards? Now I've run out of room, so I'm going to do another column over here. Bags, cookies, and brownies. Okay, so are there any other similarities here? Ooh, I saw 16. 16 is common in both of these, so I could do 16 bags. And if I did 16 bags, I would have 3 brownies. So there's my 3 brownies. And I would have 4 cookies, wouldn't I? So there's that one. Is there any other similarities here? 48, 62, 24, 30. Yeah, no, I think that's it. Oh, so I should have just squished those in. I thought there would be one more. But I think we're done. We've got the 16, the 8. 12 is not common. 16 is, we're done. 24 is not common. There we go. Okay, so here's all of our possible ways. Okay, so, wow, this is lots of really good information. That's how many possible ways we could package both of the items. So that's the end of number 3. Oh my goodness, was I off the screen? I apologize for that. I'll give you a second to take a look at that since I think I was off the screen there for a little bit. I apologize. Okay, so there they all are. There's all of our possible ways of bagging up these cookies and brownies. Okay, now number 4, what is the largest number of combination bags that Diego could make? So the largest number of bags that we came up with, 1, 2, 4, 8, and 16, was this one right here. 16 bags with 4 cookies and 3 brownies each. That's a great bag of goodies, isn't it? That's perfect for like a family or something, right? So there's our largest. How do we know that it's the largest possible number of bags? Well, because we organized our work really, really well, right? And that's a really good thing to be able to describe to your partner. How did you organize your work so that finding that answer became super easy, didn't it? Because that's really our only explanation here, is that we spent the time that it took to really organize our work along the way so that we could pull all this information together to make really good answers. Okay, so there's number 4. There's our largest number of bags that we could make with how many of each item we can put in them. Okay. Well, ladies and gentlemen, what we just did right here is what's called a greatest common factor. Okay. This is often called, and it's going to say it down here, I think, it's also called, in short, a GCF. Okay. So a greatest common factor, a GCF. Okay. The greatest common factor of 30 and 18 is 6. What do you think the term greatest common factor means? Well, if we know what factor means, it's all those numbers that we can multiply by to equal what we want them to equal, right? And if we want the greatest of those, just like this one, we want the biggest number of bags possible, then I think what it's saying here is if I list out all the factors of 30, and if I list out all the factors of 18, just like we did with the cookies and the brownies, if I list out all the factors and find the biggest one they have in common, then that must be the GCF. Does that make sense? So let's try it out. Let's list out the factors of 30. And here's a faster way of writing those out. We did the factor pairs earlier, right? Where we listed them all out like this, but there's a faster way. The factors of 30 are, yes, 1 and 30. So I'm just going to list them out in a list here. 2 times 15. 3 times 10. 4 does not go in, but 5 times 6. And then 6 times 5, we're already done. So there's my list of factors. Once I get to one I've repeated, then they're going to just match up again, aren't they? So there's all my factors of 30. Now I need all my factors of 18. Well, 1 times 18, 2 times 9, 3 times 6, 4 doesn't go in, 5 doesn't go in, but 6 goes in 3 times. So I've already hit my other side, so I've spaced these out more than I needed to, but that's okay. So there's my list of factors for 18. Does that make sense to everybody? I just listed the factors. Okay. Now that I look at this list, if I'm looking for the greatest that they have in common, let's look for what they have in common. They have 1s in common, they have 2s in common, they have 3s in common, they have 6s in common, and that's it. So which one of those is the greatest? 6. It is literally the greatest common factor. Okay? So that's what that vocabulary means. Okay? So in number 2, this is what we're going to do. We're going to find that greatest common factor of 21 and 6. Okay? So first we have to find all the factors, and then we can identify which one of them is the greatest. So we're going to do it this same kind of way. Takes up way less space, right? So let's list all the factors of 21. 1 times 21. I like to go to give myself some space between those. Hopefully I give myself enough space. Does 2 go into 21? Nope, but 3 does. 3 times 7 is 21. 4 does not go into 21. 5 does not go into 21. 6 does not go into 21. 7 does not go into... Oh, 7 does go into 21. So guess what? I'm going to actually shorten that list up, because that's all the factors of 21. 21 doesn't have very many. 1, 3, 7, and 21. Now, what are the factors of 6? 1 and 6, and 2 and 3. And that's it. Right? Can you think of any other factors of 6? I certainly can't. Okay. So now we need to find the common factors. Well, 1s are common. 3s are common. And that's it. Nothing else do they have in common. So what's my greatest common factor, or my GCF? Is the greatest of these is 3. So the greatest common factor of 21 and 6 is 3. Okay? How are we feeling about greatest common factors so far? Hopefully that came together pretty straightforward. Let's try another one. Okay? Then we'll for sure get this. Find all the factors of 28 and 12, and then identify the greatest common factor of 28 and 12. Okay, so the same thing as number 2. We're going to do it again, but with different numbers. So once again, we're going to list out all the factors of 28. 1 times 28, 2 times 14, 3 doesn't go into 28, but 4 does. 4 times 7 goes into 28. 5 doesn't. 6 doesn't, but 7 does. So there it is. I'm going to scoot 7 over to fill this hole in a little bit. So 7, 14, and 28. There's all my factors of 28. Now I do the same thing for 12. List all my factors of 12. 1 and 12, 2 and 6, 3 and 4, 5 doesn't go in, and I've already got 6, so we're done. Okay, there's all the factors of 12. Now I want to find the common factors. Well, 1 is always common, right? 2 is common in this case. 4 is common in this case. 7 is not, 14 is not, 28 is not, 3 and 6 are not. So I think we're done. So which one is the greatest common factor? Well, the greatest of those is 4. So the greatest common factor of 28 and 12 is 4. Now, some of you at this point may be thinking, could I do that in my head and not have to list them all out? And the answer is yes, but be super careful when you do that to double check, right? Listing them all the way out is just a safe way of making sure we don't miss anything, right? All right, let's go on to number 4. A rectangular bulletin board is 12 inches tall and 27 inches wide. Elena plans to cover it with squares of colored paper that are all the same size. The paper squares come in different sizes. All of them have whole number inches for their side lengths. So we've got a bulletin board. We want to cover it with squares of paper. She's making some kind of a cool background on her bulletin board, right? So what side length of the largest square that Elena could use to cover the bulletin board completely without gaps or overlaps? So she wants to cover this thing perfectly with nothing, no white showing in her bulletin board. I guess brown is what bulletin boards are. She wants to cover it completely with paper. But she wants to use the biggest size square possible. Well, guess what, guys? That's exactly what we've been doing. That's the greatest common factor. Squares are going to have the same lengths on the sides, on all sides, right? So if we find the greatest common factor of a 12-inch by a 27-inch bulletin board, then that should give us the size of our square, shouldn't it? Okay, let's try it out. Let's find the factors of 12, and then we will find the factors of 27 and see if we can figure this out. The factors of 12 we actually did in number 3, didn't we? So we can just list those out. 1, 2, 3, 4, 6, and 12. And the factors of 27 are 1 and 27. 2, oh, I don't know why I have a comma there. 2 does not go into 27, but 3 does. 3 times 9 is 27. 4 does not go in there, 5 does not go in there, 6 does not go in there, 7 does not go in there, 8 does not go in there, but 9 does. So guess what? There's only those 4. So I'm going to shorten up my list. Sometimes that happens, right? You think there's going to be more than there is. Okay. Now I have my 2 lists. I could do a 1 by 1 square. See how this works? I could do a 3 by 3 square. Or could I do anything else? No, nothing else is the same. Again, the sides have to be the same, don't they? So I could do a 1 by 1 square or a 3 by 3 square, but there's no other possibility. So the biggest one I can use is a 3-inch, whoops, goodness gracious, is a 3-inch by 3-inch square. That is my GCF, isn't it? So that's the biggest square I can use, okay? Now in this problem, it said to explain or show, and I think we did a pretty good job of showing, right, our work. We drew a little picture, we did the math over here. I think we did a pretty good job. So I think we can call that one done, okay? Part B, how is the solution to this problem related to greatest common factor? Well, I kind of gave that hint away early on, right? That's exactly how we figure that out, is by finding, okay, which dimensions do they have in common? Because we know a square has to have this is the tall, the height, and this is the width, right? They have to be the same. They have to have those in common or else it's not a square, right? So we have to find those common factors, and then in order to get the largest one, we needed to look for the biggest of those common factors. So that's exactly what we did here. We found the GCF, right? We found the largest height and the largest, whoops, L-A, oh, I can't write. Largest width that they had in common, right? Because it has to be a square, right? Which is the GCF. That's exactly what we just found, right? My pencil is really dull. I don't know. It's a mechanical pencil, so I can't do much about that. That is exactly what we just found, right? Okay. Guess what, ladies and gentlemen? I think we might be done with this activity, this lesson. Because all we have now are the Are You Ready for More optional challenge problem, right? So there's our optional challenge problem and then our summary page, right? Again, our glossary term was common factor, and I'm going to say, oh, yep, there it is right there. And then the greatest common factor, or the GCF. is our other vocabulary word. So there's our 2 vocabulary words for this time. I hope we understand both of those. If not, the definitions in the glossary are really great too. And there are some examples next to those definitions that should help. Okay, so very, very good. We are now done with lesson 16 and ready to do our practice problems. So I will give you a little bit to make sure you go back and double check that you finished your homework problems, and then we'll dive into this in just a second. Good job, guys, and as always,
do your best, because you deserve your best.
All right, we are ready to start lesson 16's practice problems. Let's dive in with problem number 1. A teacher is making gift bags. Each bag will be filled with pencils and stickers. The teacher has 24 pencils and 36 stickers to use. Each bag will have the same number of each item, with no items left over. For example, she could make 2 bags with 12 pencils and 18 stickers each. What are the other possibilities? Explain or show your reasoning. Now, this looks really familiar to me. I think this is exactly the same kind of problem we did in our lesson today with the cookies and brownies. Remember that? Where's my other page here? There it is right there. Remember our cookies and our brownies? This is exactly the same kind of idea. We want to bag up, this time, stickers and pencils, just like we bagged up cookies and brownies. So we're going to take what we did in our lesson today and do the exact same thing for now, these pencils and stickers. So let's think of all the different possibilities here. So once again, I'm going to do bags of pencils and then bags of stickers, right? We're going to find all of our factor pairs, and then we'll compare those and find the greatest common factor, right? Okay. So let's do this. For 24 pencils, I could do 1 bag of 24. Does that make sense? I could do 2 bags of 12. I could do 3 bags of 8. I could do 4 bags of 6. I couldn't do 5 bags. That's a B. But then 6 bags of 4. Okay, so this would go either direction, right? 6 bags of 4 or 8 bags of 3, either direction. Okay. For the stickers, I could do 1 bag of, let's see, we have 36 stickers. I could do 2 bags of 18 stickers. I could do 3 bags of 12 stickers. I could do 4 bags of, 4 bags of 9. 5 doesn't work, but 6 bags of 6. Oh, there's my perfect square factor pair. So I know I'm done. Because 7 doesn't go in, 8 doesn't go in, but 9 does, and I already have 9. So there we go. Okay? So what I'm looking for here, these can go either direction, right? So I'm looking for the greatest common number in either list, right? So let's take a look. Which one's the biggest? Well, I noticed that, of course, 1 is common, but that's always common. 2 is common. 3 is common. 4 is common. 6 is common. 12 is common. Is there anything else common? I don't think I see anything else common. Did you find it? Did you see which one was the biggest? I think 12, right? Now, the way I wrote this out, I did it this way because it was the same as the brownies and cookies way. But do you like the list way better? I think I do too, because it's a little bit easier to find these greatest common factors. So I think our greatest common factor is 12, which means that if I make 12 bags, right? I could put how many of each thing in it? Well, if I had 12 bags, that would have 2 pencils. With 2 pencils. And 12 bags would give me 3 stickers. That's the biggest number of bags that I could make. Those would be great little prize bags, wouldn't they? Does that make sense to everybody? Oh, wait, we didn't have to find the greatest common in this one. We just had to find all the possibilities. That's why I did it that way. There's all the possibilities. We took it a step further. Well, you didn't have to do that, but now we know how to, don't we? Number 2, list all the factors of 42. Okay, here we go. We're going to list these all out. 42. Well, we know 1 and 42 are a factor pair. 2 times 21. 3 times, what is it, 14? 4, nope, 4 doesn't go in. 5 doesn't go in. 6 goes in 7 times. And then 7 goes in 6 times. So we've hit it. We've hit the duplicates. Okay, so there's all the factors of 42. Which is the greatest common factor of 42 and 15? Well, in order to find the greatest common factor, finding the factors of 42 isn't enough. I have to also find the factors of 15, don't I? So let's find the factors of 15 so that we can compare. Well, 1 times 15 equals 15. 2 doesn't go in, but 3 does 5 times. And that's it, because 4 doesn't go in, but 5 we've already got. So those are the factors of 15. Now I can find the common factors. Well, 1 is common. 3 is common. And that's it. So 3 is the greatest common factor. The GCF is 3 in this case. Okay. What is the greatest common factor of 42 and 50? Well, we need to find the factors of 50, don't we? Before we can compare 42 and 50. So let's do the factors of 50. The first factor, of course, is 1 and 50. 2 and 25. 3 doesn't go into 50. Neither does 4, but 5 does. 5 times 10. 6 doesn't, 7 doesn't, 8 doesn't, 9 doesn't, 10 does, and we already have 10. So there they all are. They're spaced out weird. Maybe I'll rewrite them. 10, 25, and 50. Okay, so now we are comparing to find the greatest common factor of 42 and 50. We have to compare these two lines. Do you see that? So 1 and 1, of course, that's a common pair, but they're always common, so we really don't care about that. 2 is common. 5 is not. 10 is not. 7 is not. 14 is not. 21 is not. 42 is not. Okay, so there's not very many on this list. I think 2 is our GCF. Does he anything higher than 2? I don't. So the GCF of 42 and 50 is 2. There we go. We're done with number 2. Okay. Number 3. A school chorus has 90 6th grade students and 75 7th grade students. The music director wants to make groups of performers with the same combination of 6th and 7th grade students in each group. She wants to form as many groups as possible. What is the largest number of groups that could be formed? Explain or show your reasoning. Here we go. We need to find the greatest common factor, don't we? We've got 90 6th graders and 75 7th graders. So let's find those two numbers. And this assignment didn't give us much room to work. I hope your workbook did better than my papers did. Not much room to work here. I'm going to put the 90 factors up here, and I'll put the 75 factors down here. I like them to be on top of each other because it's easier to compare, right? So the factors of 90 are 1 and 90, 2 and 45, 3 and 30, 4 doesn't go in, 5 and, what is it? I don't know how many times 5 goes in, but it's got to go, what? 18 times? Got to be. Yes, 18 times. And then I'm squishy. Oh, I hate it when I get squishy because now I got to give myself more room because I've still got to fit 9 and 10 in there. 9 and 10. So now let's go back. 10 times 9 18 times 5, 30 times 3, 45 times 2, and 90 times 1. Okay, so there. Now we got our list back. Now for the factors of 75. We have 1 and 75. 2 does not go in because it's not even. 3 does because 3 times 25 is 75. 4 does not, but 5 does because 5, times 15. 6 does not, 7 does not, 8 does not, 9 does not, 10 does not, 11, 12, 13, 14, 15. I think that's all of them. So I'm going to combine these to make a nicer looking list here. Okay, now we have all the factors of 75. Now, in order to find the largest number of groups that could be formed, we need to find the greatest common factor, the GCF of 90 and 75. Let's find the common factors first. We have 1 are common, 3s are common, 5s are common. Is that it? I don't think I have anything else in common, so I think 5 wins. What do you guys think? I think our GCF is 5. Well done, well done. If that many groups are formed, how many students of each grade level would be in each group? Okay, if we have 5 groups, okay, then that means that we look at 5 times what equals 90. Does that make sense? So what is its pair? So if we pair these up, 2 and 45, 3 and 30, 18 and 5. There it is right there. 18. There would be 18 6th graders. And what pairs up with 5 here? 1 and 75, 3 and 25, 5 and 15. And 15 7th graders. There you go. Okay? So with 5 groups, there would be 18 6th graders and 15 7th graders. Here are some bank transactions from a bank account last week. Which transactions represent negative values? So this is a review of our negative and positive stuff. Monday, $650 paycheck deposited. Do we know what the word deposited means? That means it was put into your bank. You were paid that money. So that's a positive. Right? So which ones represent negative? Not Monday. It's positive, isn't it? Tuesday, $40 withdrawal from the ATM at the gas pump. Well, withdrawal is the opposite of deposit, isn't it? So this is taking money out. So Tuesday is definitely negative. So there we go. Tuesday is negative. How about Wednesday? $20 credit for returned merchandise. Oh, if I return merchandise and I get $20, that's positive. I gained $20. Credit is a positive thing, isn't it? So Wednesday is not negative. Okay? But there's more, so let's keep going. We're now on Thursday. On Thursday, we had $125 deducted for cell phone charges. Well, deducted means it was taken away. So that is negative. So Thursday is negative. Okay. How about Friday? $45 check written to pay for a book order. Oh, if I wrote a check and paid for something, that means I lost that money, right? So this is definitely negative. So Friday is also one of our answers. How about Saturday? $80 withdrawal for weekend spending money. Oh, there's that word withdrawal again. So it must be negative. So Saturday is negative. Sunday, $10 cash back reward deposited from a credit card company. Oh, look at that. It's a reward and it was deposited. So once again, deposited is a positive thing. So that means that Sunday is not negative. Okay, so there are 4 answers to this one: Tuesday, Thursday, Friday, and Saturday. So I'm going to go ahead and write those out. Tuesday, Thursday, Friday, and Saturday. I abbreviated those. Those are my 4 answers: Tuesday, Thursday, Friday, and Saturday. Okay? Very, very good. On to number 5. Finding the quotients. Okay, dividing fractions. It's been a while since we've done this. Let's make sure, remember, when we divide fractions, we flip and multiply, right? Because we have to divide by the denominator and multiply by the numerator. So we now have 1/7 times 8 over 1. There's nothing I can simplify, so the answer is just 8/7 or 1 and 1/7 if I simplify that to a mixed number. Okay? Part B, again, I'm going to flip the second fraction. So we have 12/5 times 5/6. There is stuff we can simplify here. 5 is a common factor. Oh, look at that. Back to common factors. This is so cool. 5 is a common factor, so those go in once. We also have a common factor here of 6. 6 goes into 6 once, and 6 goes into 12 twice. So look how easy the math became there. 2 over 1 is just 2. Here we go with part C, 1/10 divided by 10, but remember that is a 10 over 1. So this turns into 1/10 times 1/10, which becomes 1/100th. There's our answer there. Part D, 9/10 times, again, we flip it. It'll also be 9/10. Nothing to simplify, so this just becomes 81/100ths is our quotient for that one. How did you do on those 4? It's been a while since we've divided fractions, but look how our common factors came in handy. That was super great. Last problem on tonight's homework, number 6. An elephant can travel at a constant speed of 25 miles per hour, while a giraffe can travel at a constant speed of 16 miles in a half an hour. Which animal runs faster? Explain your reasoning. Now, the first thing I noticed in this problem is that the per number is different, right? In order to compare these, I need something like per hour, not per half hour. So let's change these so that they're the same. Either make this per half hour or make this per hour. And I think the easiest way to do this is just to double this, because then it will be an hour, right? 2 half hours equals 1 hour. So let's times this by 2, which means we have to times 16 by 2. 16 times 2 is 32 miles per hour for this one, compared to 25 miles per hour for the elephant. So which one's faster? Ah, look at that. The giraffe is actually faster, isn't he? So which animal runs faster? The giraffe. My pencil. At 32 miles per hour, where the elephant was only going 25 miles per hour. Okay. How far can each animal run in 3 hours? Okay, so the elephant, for 25 miles per 1 hour, if I times that by 3 hours, that would be 75 miles in 3 hours. And the giraffe can go 32 miles in 1 hour. So if I times that by 3, that would be 96 miles. So just like we expected, the giraffe can go further because he's going faster, isn't he? And that's the end, ladies and gentlemen. So the elephant can go 75, the giraffe can go 96. The giraffe is the answer there, and we're done with number 6. Congratulations, you just finished lesson 16. We are ready now for our Check Your Understanding quiz. Well on our way to finishing up this unit. Well done, guys. You've been working hard. Keep up the good work. And as always,
do your best, because you deserve your best.